show solutions on a sample problem number 3, which involve biaxial bending with torsion. Okay, so as you can see from the given problem, we're asked to check the beam shown in the figure in compliance with the AISC specification. That means yung code provision natin on biaxial bending. Lateral support is provided only at the ends of the simple beam, sa dulo-dulo lang. Tapos the steel used is A992 with Fy of 345 megapascal. The 90 kilonewton service loads are 30% dead load and 70% live load. Okay, then considering beam self-weight and assume compact section, so we're asked to check for the adequacy of the beam. So again, you have a simple beam with two concentrated loads, 90 kilonewton, pareha sila. Pero yung 90 kilonewton, hindi siya vertically applied. If this is the wide flange beam, hindi siya vertical na nakaganyan. So sa halip, naka-incline siyang ganyan. So dalawang 90 kilonewton naka-applied on this direction, which is 4 vertical tsaka 3 horizontal yung slope. So 3, 4, 5 triangle yung slope niya. So ibig sabihin, kukuhain natin yung vertical component nito. That is bending about x. That will cause bending about x. Tapos kukuhain ko rin yung horizontal component niya. That will cause bending about y. Pero kung kukunin mo yung horizontal component niya, diba, yung horizontal component will not pass through the shear center. Nasa ibabaw eh. So therefore, magkakaroon siya ng torsion. Okay, so this problem is may torsion na siya. Okay, so the properties of the section are also given, taken from the steel manual. Okay. Okay, so first, to check for the adequacy, so we have to satisfy this interaction equation. No? So bending about x plus bending about y should be less than or equal to 1. So take note na may over 2 rito. May over 2. So ibig sabihin yung over 2 na yun because of the presence of torsion. So the capacity on y-axis bending is reduced or is being half. Okay, kaya may over 2 doon. So first we solve for the ultimate load, 1.2 of dead load plus 1.6 of live load, since the 90 kilonewton is just service loads. So 1.2 of dead load, and dead load is only 30% lang daw ng 90. Tapos yung 70% daw doon ay live load, kaya minultiply natin siya. So this would be the ultimate load. So 133.2 kilonewtons na. Then hindi ba't naka-incline siyang ganyan? So ang slope niya is 3 horizontal, 4 vertical, so 5 yung triangle. So we're going to get the vertical component. So yung vertical component, tinawag ko siyang P sub x. Tapos yung horizontal component, tinawag ko siya as P sub y. Okay, P sub x kasi siya yung magiging vertical component that will cause bending about x. Tapos yung py naman, kasi siya naman yung magkakos ng bending about y. Okay? So yung px would be yung pu multiplied by 4 over 5. So ito yun. Tapos yung py, pu times 3 over 5, the components. Tapos as sinabi sa problem that we have to include also self-weight. So the self-weight is 134 kg per meter. Kinuha ko to sa steel manual. Tinimes ko ng gravity, 9.81. Dinivide ko ng 1,000 para siya maging kilonewton. Tapos minultiply ko siya ng 1.2 kasi this is a dead load. Factored load. Factor load for dead load, 1.2. So I got W sub U, yan yung pinaka-self-weight, 1.577. So di bali, nasaan ba yung dead load? Diba kapag ganito yung section mo, ang dead load mo na dito, in this direction. That causes bending about X. So again, ang direction ng self-weight is bending about X lang. Wala siyang contribution sa bending about Y yung self-weight. Kasi nakatayo yung beam eh. No? Nakatayo yung beam. So ang self-weight niya is bending about X lang. So yan. So bending about X. Okay. So ganyan yung magiging beam natin. No? So meron tayong self-weight. Tapos meron tayong PUX tsaka PUX din dito. So yan yung considering bending about X. So due to those uniform load and concentrated loads, I solved for the reaction of the beam. So I got 109. Then ano yung MUX? Yung MUX is the maximum moment eh. Oh, hindi to katulad nung sa Perlin. Sa Perlin kasi laging WL²/8 kasi uniform load lang ang load nila. Dito, hindi siya parang Perlin kasi meron tayong concentrated load na given sa problem, yung PUX. So the maximum moment would be taken, una, pwede kayong mag-drawing ng shear and moment diagram. From the moment diagram, very safe na makikita mo ron kung ano yung maximum moment from the diagram. So yun na yung MUX. Pero dito, ang ginawa ko na lang, because of the symmetry of the section, because of the symmetry of the loadings, so I could say that the location of the maximum moment would be at the midspan. So doon yung maximum moment midspan, so I cut the section there and isolate. So cut the beam and isolate. So the maximum moment there would be the reaction times 175, yung distance from the midspan. Tapos yung PUX times the distance from the midspan. Tapos yung uniform load, WL/2 times L/4. Kaya naging WL²/8. So ito ngayon yung due to uniform load naman. So I got maximum moment to be 108 kilonewton meter. Yun yung MUX naman. Now, paano pagkuha ng MUY? Again, MUY. Pagka MUY, ano yung load na i-consider mo? Wala na yung uniform load kasi yung uniform load na nandito eh. Pagdating sa bending about Y, wala na yung uniform load, kundi yung ano lang, yung component na lang nung concentrated load na dalawa. Kaya pagkuha ng MUY, okay, so yan yung pagkuha ng MUY na. No? So due to PUY tsaka PUY, wala nang uniform load. So pagkuha ng MUY would be, I solve for the reactions muna. So the reaction times 1.75 because I know that the maximum moment is at the midspan. Tapos yung PUY, 79 times the distance. So I got 79.92 to be the maximum moment due to the factored loads. So okay na tayo sa numerators, 'di ba? Sa mga numerators, okay na tayo, MUX at MUY. So let's go into the denominators naman. Yun yung mga nominal strength capacity. For capital M and X, so since it was given that the section is compact, so no need to check the compactness. So ang gagawin na lang natin is lateral support condition. So yung LB natin is 3.5. Bakit 3.5? Bakit 3.5? Eh, diba sabi sa problem, the beam is 3.5 meters yung length. Tapos wala naman daw lateral support. Ang mga lateral support lang natin dito raw sa beam is yung dulo-dulo. Okay? So walang lateral support na nakalagay sa gilid niya. So, di bali ang LB natin is yung full length na 3.5 meters or 3,500 millimeters. I solve for LP. Okay? So, ano ba sa LP? 3.9. So, sa LP pa lang, less than na siya. Ibig sabihin, kapag yung LB mo is less than LP, ibig sabihin, laterally supported na siya. You don't need to solve for LR. Nagsasolve lang tayo ng LR kapag yung LP nag-greater than dun sa LP. Okay, pero pagka yung LB less than LP, hindi mo na kailangan mag-solve ng LR. So automatic it would be laterally supported na siya. So yung MNX natin pagka lateral supported would be FYZX. So FYZX. So ito na yung MNX natin. So okay na tayo dyan. Next, how about MNY? MNY. Again, compact section na yung section natin. So, ang MNY natin would be simply FYZY. FYZY, section property. Then, i-check mo lang siya sa 1.6 FYSY. 451. So, pasado naman, no? So, yung 427, less than naman siya sa 451. So, sabihin, okay naman yung MNY natin. So, we got the MNY, 427. Now, so we will just substitute everything in the interaction equation. Substitute everything. So yan, don't forget yung over 2 natin. So yung over 2 natin because of torsion. Tapos yung resistance factor natin for flexure is 0.9 pa rin. So substituting values, so yan lahat yan. And the value of the interaction equation turns to be 0.55 which is less than 1. So that means the given section for this beam is safe. No? Kasi it's less than 1. So medyo hindi pa siya ganun ka-economical kasi 0.55 eh. So you could actually reduce the size of the section para siya maging economical. Okay? So ganyan yung pag-analyze ng beam natin which experiencing biaxial bending with torsion. Okay? So I hope you have learned out of this discussion. So thank you.